Hi, my name is Danielle. I'm a machine learning solutions engineer at Google Cloud Advanced Solutions Lab. My area of focus is reinforcement learning, and I can't wait to share it with you. Reinforcement learning is a category in machine learning that explores how rewards over time impact a learner in an environment. For instance, how does a video game player master Mario? How does a robot find its way through a maze? Or, in our case, how does a trader optimize assets? All of these deal with the idea of delayed gratification, that our actions now can impact our state in the future. In this session, we'll go over reinforcement learning at a high level. I'll save the mathematics and algorithms for next time. Mainly, I'd like to share with you what's needed to get started with reinforcement learning and what it can accomplish so you can decide if this course is right for you. To start, let's go over how reinforcement learning, or RL, is different from other machine learning techniques. Reinforcement learning is a part of artificial intelligence, which is how do we teach machines how to solve problems in a way that's similar or better than humans? Within that, we have machine learning, which is how do we teach machines to learn rules based on data and experiences? And inside machine learning, there are three major fields. There's supervised learning, which means we have a bunch of data with inputs and outputs, and we want to help the machine learn a function which takes those inputs and predicts the corresponding output. There's unsupervised learning, which means similarly, we have a bunch of data. However, the data isn't broken up into inputs and outputs. Instead, our goal is to help the machine learn patterns in this data and find a way to group like data points. Finally, we have the topic of this class, reinforcement learning. So let's try a hand at our pattern recognition skills. If supervised learning has lots of neatly labeled data, and unsupervised learning has lots of unlabeled data, any guesses for what kind of data does reinforcement learning have? It actually doesn't have previously gathered data. Instead, we'll run simulations and use our experiences as the data. We're going to create an intelligence called the agent that interacts with what's called an environment. It's a purposely vague term that means anything that gives us an observable state. When we act based on that state, the environment will return a reward, which can be positive or negative. I just threw a bunch of vocabulary at you, so let's take a moment to break each of them down. This is what our training loop is going to look like. Over here on the left, we have our happy-looking agent. This is the intelligence that we're going to help learn and observe the world. On the right, we have our environment, which is the world our agent is going to interact in. To begin our training loop, the environment is going to give the agent a state. This is what the agent can observe about the environment based on its current position. Based on the state, the agent is going to determine what action it should take. This should put the agent in a new state, completing the loop. Additionally, after performing an action, the agent will get reward information. It can be positive or negative. As I said before, these definitions are purposely vague, so let's see them in different contexts. If this were a video game, the player would be the agent, and the game would be the environment. The state information would be the current pixels displayed on the screen, and the player's actions would respond by pressing buttons on the controller. The reward would be any points gained by moving from one state to the next. For trading, our environment would be the stock market, and the trader would be the agent. The state would be the current statistics about the market, the current weekly rolling average, the previous day's highs and low, all that great stuff Jack and Rom have taught us. Our actions would be to go long or short, and on which stocks. And our reward would be our profit and loss explained. We're going to be building out some equations later based on these concepts. State is represented by S and action by A. Every time we complete a state-to-state transition, that's going to increment our time counter, or T, by 1. When we complete that transition, we might get a reward, or R. Some of you might be wondering about sequence modeling with the REMA and LSTMs. Like reinforcement learning, these algorithms also deal with time. The key difference is that sequence models will tell us what the next value is in a series. For instance, if I have a high and low for the past week, can I create a formula that predicts what tomorrow's high lows are going to be? It's then up to the human to take that number and figure out how to act on it. For instance, which stocks should be bought or sold and by how much? Reinforcement learning is not going to tell us tomorrow's high lows. Instead, it will do interpretation to figure out how to act. It will figure out which stocks to buy and the quantity. Now that we know how RL works at a high level, let's see what it can do. Some students ask me, Danielle, is there really an intelligence we're building? Can we really make machines that learn how to problem solve like people do? And my argument to that is, how can we prove humans are not superpowered machines? When we build algorithms for supervised learning or unsupervised learning, don't get me wrong, they're impressive. But for reinforcement learning, those algorithms are only a part of what we need to build for our agent. For instance, supervised learning might use a neural net to solve a problem. That would be like a human's prefrontal cortex trying to solve a problem. But there are many more components to an agent. We may build in a sense of curiosity to help it explore and better understand its environment. The agent will need to be able to react, as in, not only does it need a way to take in environmental stimuli, in turn, it needs to interact with the environment. We might also give it memory so it can continue to learn from past experiences. Many of the breakthroughs in reinforcement learning have to do with better understanding how humans and animals learn. It is a beautiful art to be able to quantify how we think. In this class, we'll be able to mathematically represent such sayings as, if at first you don't succeed, try again. Do one thing every day that scares you. Practice makes perfect, and why do we fall? So we can learn to pick ourselves back up. Pretty much anything you saw as a motivational poster in your high school counseling office, we will show has mathematical substance. All in all, though, I wouldn't be worried about these intelligences taking over the world anytime soon. Of course, intelligence is already tricky to quantify, but one rough measure would be the number of forebrain neurons. Here, we have a number of animals laid out on a logarithmic scale. On one end of the spectrum, we have the common house mouse with 14 million neurons. On the other, we have a long-finned pilot whale at 37 billion. Us humans are sitting pretty at 15 billion. Any guesses on where AlphaGo would be? The machine that beat the world's top players at Go? How about here, almost off-screen and to the left of the house mouse? AlphaGo has millions of neurons, so while impressive, even the world's largest game-playing neural networks have a way to go before catching up to us humans. But if AlphaGo is so much smaller, how is it able to beat the world's best players? There are a few reasons for this. Humans are designed to do so much more than play Go. Our bodies are made to find the next good meal or where to find a hot date. AlphaGo doesn't have to worry about any of that. Every networking fiber of its body is made to go and excel at the game of Go. It isn't just some giant neural network that was thrown into playing many matches. It's a combination of a few algorithms, some machine learning, some good old-fashioned game theory, and it goes to show that it isn't always the largest number of neurons needed to be best at solving the problem. It's how those neurons are used. How about the intelligences we'll be making in this class? They'd be off-screen with things like snails. Still, we're going to make some pretty smart intelligences for only a few hundred neurons. At the end of it all, we'll be proud robot parents. To finish this intro, let's get hyped over some of the successes that reinforcement learning has had. In the games department, reinforcement learning could beat the world's best human players in chess and backgammon. In video games, RL bots have had success with many Atari games, StarCraft, and League of Legends. For finance, much of its challenges can also be phrased as a game, although one with money on the line. JP Morgan has an RL agent that they use for trading, and Stanford researchers show success using RL for currency exchange. There are many other uses for RL that aren't games and finance. Much of the early history of RL was focused on robotics, like how do we help a robot navigate a maze? Today, that manifests itself in self-driving cars. There are some pretty creative uses out there as well, like how Netflix frames movie recommendations as a reinforcement learning problem.